This section builds the definite integral from rectangle approximations. We will move from rates and estimated totals to Riemann sums, limits, signed area, and accumulation. It is a long journey made entirely of very thin rectangles. These objectives connect numerical approximation, algebraic limits, geometry, and applications. By the end, the integral sign should represent an idea rather than merely an unusually tall letter S trying to impress everyone. For a constant rate, the accumulated quantity is the area of a rectangle, height times width. This is comforting because rectangles remain one of the few things in calculus that behave exactly as advertised. A curved region does not have an immediate length times width formula, so rectangles serve as approximations. We make them thinner until the approximation becomes exact, which is calculus saying, "Fine, I will use my most powerful weapon, namely limits." Each rectangle has width delta x and height determined by a representative point. Adding all rectangle areas gives a Riemann sum. It is the mathematical version of dividing a giant assignment into tiny tasks and then submitting all of them at once. The rectangle height can come from the left endpoint, right endpoint, or midpoint. All three methods use the same widths but sample different locations. Each rectangle touches the curve at its left endpoint. Because the function is increasing, the rectangles lie mostly below the graph, so the estimate is smaller than the actual area. Now each rectangle touches the curve at its right endpoint. For this increasing function, the rectangles extend above the graph and give an overestimate. The right endpoints did extra work, although nobody asked them to show off. The midpoint method samples the center of each subinterval. The resulting rectangles balance some of the excess and deficiency and are often more accurate. Midpoints are the diplomatic students of numerical integration. They insist that everyone meet halfway. The first step is always to compute the common width and list the correct representative points. A small mistake here infects every later calculation, much like arriving at the wrong classroom but confidently taking notes anyway. The left sum is 3.75 and the right sum is 5.75. Monotonicity explains which one lies below and which lies above the exact area. For an increasing function like this one, the left sum is an underestimation and the right sum is an overestimation. For a decreasing function, it is the other way around. The midpoint estimate is 4.625 between the left and right sums. It improves the approximation without increasing the number of rectangles. That is like working smart rather than more. Every Riemann sum requires an interval, a number of subintervals, and a choice of sample points. Stating these decisions first prevents accidental mixing of methods. Calculus appreciates commitment, especially when choosing endpoints. Sigma notation compresses a long addition into one symbol. The index tells us which terms to include. Without sigma, Riemann sums would look nightmarishly messy. These formulas remove sigma notation before we take a limit. Linearity lets us split sums and pull out constants. Memorizing them saves time, although naturally the formula most needed on a test is the one that suddenly takes a personal day off your memory. With 8 rectangles, each width is 1/4. The staircase follows the curve more closely than it did with 4 rectangles. More rectangles bring more accuracy and more opportunities to forget which endpoint you are using. With 16 rectangles, the staircase is noticeably closer to the curve. The gaps shrink as delta x decreases. The rectangles are now so thin that they resemble the margins students leave when they run out of notebook paper. With 32 rectangles, the approximation nearly traces the curve. As the number of rectangles grows without bound, their widths approach 0. The rectangles are becoming infinitesimal, which is calculus for too small to blame individually. The definite integral is the limiting value of Riemann sums as the rectangles become infinitely thin. It is one number, not a family of functions. Infinity does the heavy lifting here and, surprisingly, never asks to be added to the payroll. Right endpoints give a convenient explicit formula for x sub k. Continuity guarantees that the Riemann sums converge to a definite integral. It is one of the nicer guarantees in mathematics, unlike this quiz should only take 10 minutes. For the interval from 0 to 2, delta x is 2 over n and the right endpoint is 2k over n. Substituting into the function gives the rectangle heights. This setup is short, but like reading the instructions, it prevents a surprisingly large number of disasters. The summation formula converts the expression into a function of n. As n approaches infinity, 1 over n vanishes and the value is 8. 1 over n quietly leaves the calculation, much like half the class 5 minutes before the lecture ends. The lower limit is 1, so the right endpoints begin with 1 plus 2k over n. Expanding f of x sub k produces constant k and k squared terms. The algebra is growing, but it has not yet requested its own postal code. We split the sum, apply the formulas for k and k squared, and simplify. The expression now contains only n, so the sigma notation has completed its job. Sigma can go home now. Take care, sigma. Taking the limit removes every 1 over n term and leaves 50 over 3. The infinite process produces a finite answer, which is more than can be said for some committee meetings. The interval has length 3, so delta x is 3 over n. Right endpoints begin at -1 and advance by 3 over n. Negative lower limits are harmless once they are included, unlike negative marks, which students notice immediately. Expanding the cubic creates 4 types of terms, so all 4 summation formulas will be needed. This example invites the entire formula family to the party and still expects us to clean up afterward. Multiplying by delta x changes each denominator and prepares the expression for the summation formulas. Keeping the powers of n organized is essential. They reproduce quickly when nobody is watching, rather like unread messages in the class group chat. After applying the formulas, every sigma disappears and the result is expressed entirely in n. The simplification is lengthy but systematic. It is less about inspiration and more about keeping your algebraic desk tidy. The limit equals 3/4. Although the individual terms are large, cancellation leaves a small result. This is the algebraic equivalent of checking your bank account after tuition. A lot happened, but surprisingly little remains. These 6 steps provide a dependable template for every right endpoint calculation. Following the order prevents missing factors and misplaced endpoints. It is the calculus equivalent of a recipe, except nobody gets to eat the final integral. An indefinite integral produces a family of functions, while a definite integral produces one number. The fundamental theorem of calculus will connect them next. They are related, but they denote different concepts. Area above the x-axis contributes positively and area below contributes negatively. The integral records net area, so regions can cancel. The graph is keeping a balance sheet, and apparently even geometry has accounting needs. The larger triangle lies below the axis, so the net integral is -5/2. A negative integral does not mean negative geometric area. It means the below-axis region won the tug of war. Net area allows cancellation, whereas total area counts every region positively. The absolute value flips below-axis pieces upward. Integrating a rate over time recovers an accumulated quantity. The units confirm the interpretation because time cancels. The left and right estimates are 17.2 and 17.4 thousand liters, so 17.3 is a reasonable estimate. When 2 methods nearly agree, calculus experiences the rare piece of a group project with no argument. This slide collects the main formulas and interpretations. Riemann-sums approximate, limits make the answer exact, and signed area or accumulated change gives the result meaning. It is the entire section compressed into one slide, like exam review during the elevator ride to class. The definite integral begins with approximate rectangles and ends with an exact accumulated value. This prepares us for the fundamental theorem of calculus in the next lecture, which will make evaluation dramatically faster. After all this messy limit work, you would approve this majestic name given to this theorem.